you speak and then
So, hello everybody, I'm very pleased to be here. And I will first thank the organizer for the invitation to this very nice workshop. So I will show you STM measurements, experiments, done in Geneva on the CUPRATE superconductors. Okay, so phase diagram of CUPRATEs, you already saw that today, you'll probably see them many times these next days. So this is the complex diagram, not the simplified diagram that Neven just showed us. And all these phases have been quite a lot investigated backwards by STM. So for sure, many of the different points of the phase diagram have been investigated by STM. Like for example, the detection of the pseudogap as the remaining of some kind of pairing above the critical temperature. Vortices have been measured, and also these modulated phases, like the quite recently detected charge density waves, nematicity, or possibly also pair density wave, which are a focus of some big interest. And so, together with all this diagram, a lot of different scenarios have been proposed to explain the occurrence of this modulation, or possibly the mechanism of high TC superconductivity. And here I will focus on these two modulated phases, the pair density waves and charge density waves, which have been investigated by a lot of different techniques. STM also has tried to focus on these phases, and essentially when a magnetic field is applied to the sample, so the vortices are generated in the sample, the location of the vortex core is a very interesting site, because it's a place where superconductivity is destroyed, the order parameter is vanished, and then the center of the vortices revealed over the years a lot of modulation, like in this measurement in 2016, a mixed charge density wave or quasiparticle interference states seen in the course of the vortices, and more recently oscillation which were associated with the charge density wave and pair density wave, which in some scenario might be the mother order to generate the pseudogap or the charge density wave, which are seen in X-ray measurements. But the main question, and this is something we are looking for since many years, is to try to see from the vortex cores whether at some point they might still reveal some BCS behavior and be more conventional than maybe expected. So for the outline, I will show rapidly what we see by STM in vortices, like the bound state, which are predicted by BCS. And then measurements we've been doing a long time ago in YBCO, and more recently to dig out the vortices. And finally, the case of BISCO, which revealed unexpected results. So rapidly, so everybody knows that you have the vortex where the order parameter goes to 0, and the main consequence concerning the excitation that you can put inside the core is that in the case of an S-wave superconductor, these excitations should be localized. So there is a finite energy states. The spacing has been estimated, I mean, what was predicted as being of the order of delta squared, the superconducting gap over EF. And so the fact that at the center of the vortex core, the states should form a lot of these states should be visible at the center of the core, but the spacing between these states is so small, so delta square over EF, that they should not be seen individually, even at the lowest temperature. And so this has been observed in many cases of S-wave superconductors, like this niobium disulfide or diselenide, or the iron-based superconductor, where you see that the center of the vortex is associated with a zero bias anomaly. And while going away from the center of the vortex core, this central peak splits into a set of two peaks due to the increasing angular momenta. And then the splitting is seen by these STM measurements. But as I told you, the individual state cannot be seen in conventional S-wave superconductors until quite recently, where for the reason that the Fermi level is very small in this compound, this iron tellurium selenides, due to the fact that EF is very small, so now the spacing was large enough to be able to be detected. So the first localized state was detected in that kind of compound. But this is not very often the case. But cuprates are not S-wave, but D-wave superconductors. And so calculation have been performed also in that case. And long time ago by Wang and MacDonald, there was the prediction that similarly to the case of an S-wave superconductor, the center of the vortex core should also reveal a zero bias anomaly. And the evolution is actually quite similar to the one of the S-wave superconductor, with the split of this zero bias anomaly while going away from the core center. The main difference between the D-wave and the S-wave is that there are no bound states here. Whatever you go at low temperature, you will never see individual bound states. It's a continuum of states. So now, the measurements we did in '95 on YBCO, the vortice is seen here at the field of 6 Tesla, showed something which was absolutely not expected. The set of two peaks here that are measured at the center of the vortex core was obviously not the one expected, the zero bias anomaly expected at the center of a D-wave vortex core. And so for very long time, people and theories were trying to explain why a D-wave superconductor would reveal such a finite energy state instead of this zero bias anomaly. Like in this Franz and Tesanovic model, where small I dxy component had to be added, probably field-induced component, in order to get a fully gapped symmetry state and the occurrence of a finite energy states at the center of the vortex core. But this was theory, and we never had a very clear conclusion of this fact. Until more recent measurements performed also on YBCO, and where the evolution of the spectra was taken from the inside of the core to the outside of the core, so far from the core center, and where these low energy states, these subgap states, were detected almost at constant position and amplitude. So also outside the vortex core. And moreover, even without vortices, so at zero field, you see here a gap map done, acquired on the YBCO, showing that the gap magnitude is quite homogeneous in these samples. And if you take the average spectroscopic measurements over this map, you also see in zero field the occurrence of these subgap states. So obviously these subgap states are not linked at all to the presence of the vortex core. So we imagined, so we took a very simple scheme in order to understand why we have this subset of states which are actually detected everywhere on the surface very homogeneously. And so we took this model of having a non-superconducting channel from an origin that we don't know, added to a purely D-wave superconducting channel. Our estimation provides a very, very small proportion of this superconducting channel, which ranges from 10 to 20% from the total current we measure. So it should be in that picture a very small signal. And so I'm skipping the details, but by subtracting a reference spectrum, we get rid of this uniform non-superconducting channel. And we are living we are left with the differential spectra. The top line is the real measurement, and the bottom is the calculation where we took the exact position of the vortices we acquired. And then in order to be consistent with the fact that the exact position of the vortices influence all the spectroscopic signature of all the other vortices, we just generated a random distribution of vortex lines around, and this is the calculation. And you see that the match between the experiment and the calculation is quite good. And I would like to focus your attention of the different crystallographic direction. These are the traces taken along the 100 direction, while the other one here at the center on the 110 direction. And you see that the decay of this anomaly is not the same in the two different directions. And the model also predicts this one. So in this calculation, this is a self-consistent calculation. You see that the decay of the zero bias anomaly along the 100 is slower than the one. No, it's slower than the one taken along the 110 direction, which is the nodal direction. And so this behavior is essentially coming from the band structure with the Fermi velocities, which are anisotropic and determine this behavior. So now VSCO. And VSCO had the same problem. This is the spectrum taken at the center of the vortex core in VSCO. And obviously, again, in this case, there is no sign of a zero bias anomaly. But again, also here, the presence of some subgap states at the center of the core. Now, VSCO also has this vicinity of charge orders. And this is an example of the underdoped VSCO where some modulation were detected by STM. So this is part of the phase diagram. And these modulation were taken in the pseudogap regime and linked to the charge density wave. And similarly, as I already told you, the vortex halos also are usually the sites where charge modulation or conductance modulation are detected. So if you look at the spectroscopic signature of the vortex, so this is a conductance map taken at the center around a vortex, but imaged at an energy of 0. So this is the zero conductance of the vortex. You see this bright spot, meaning that the zero bias conductance increases at the center of the core. But the spectrum never showed this zero bias anomaly, which should be emerging from the background. Now, if you take the conductance map at the position of the coherence peak, the vortex appears as dark, since the coherence decreases at the center of the core. But interestingly, if you plot the conductance map at the position of these subgap states, the ones which are seen at the center of the core, you reproduce the conductance modulation which were associated with some QPI or charge density wave. So there is an indication that this subgap state, at least in VSCO, we see no modulation in YBCO, that the subgap states are more or less linked to the conductance modulation which are seen in the vortex cores. Okay, so the recent measurements we've been performing were focusing on the portion of the phase diagram where the pseudogap and all these charge density wave modulation were absent, seen by other techniques. And so we focused on the heavily overdoped VSCO crystal, where the TC is 52K, and obviously if you make the temperature-dependent measurements, you see that above TC there is no sign of pairing, of opening of a gap. So there is no pseudogap as expected in the compound I will show you now. And so we first started measurements at 3 Tesla. And the vortices, 3 different vortices shown here, or 6, sorry, all show that kind of conductance modulation, which were, I reported before, and which were in some cases related to the charge density wave state of the compound, depending on the doping, or quasiparticle interference. But so we are now here on the very overdoped side of the phase diagram, so it's likely not possible to link this modulation to the charge density wave. And moreover, when you take 3 minutes, when you take the spectroscopy across the vortex core, again here there is no sign of the zero bias anomaly, and the presence of some subgap states are again detected. And the dispersion of this pattern, so at different energy, the period of this pattern varies, so there is a dispersion, meaning that these modulations are essentially due to quasiparticle interference or Friedel oscillation. So now, these were high field measurements. We know that the vortices interact each other, so that the density of states of all individual cores might be affected by the presence of surrounding vortices. So we decreased the field to 0.16 Tesla. And now this is the picture we get from 3 different vortices, where in some cases there is a remaining modulation of the conductance, but in most of the cases there is no more clear pattern of the conductance seen at high field. And now if you take the spectroscopy across these cores, so it's the same compound, same doping, just the field which is reduced, you get back the zero bias anomaly which is predicted by the BCS. So this is the real first time where we observe what is predicted by the Wang and MacDonald calculation. But this is now done at very low field and on the heavily overdoped side of the phase diagram. So again, so we check the directionality, which is similar to the one I showed you before, along the nodal or not nodal, anti-nodal direction. And interestingly, we also checked whether by removing the vortex and just putting the field to 0 at the exact same position, so it's atomically same position in both cases, when the vortex disappears, we recover the expected spectroscopic signature of the superconducting state. So it's not the peak we see in the vortex is for sure not linked to any doping, impurity or whatever defect which could produce this behavior. Okay, maybe I should just summary by showing you that most of the reports on spectroscopy of vortices in the CUPRATE and especially on BISCO have been performed at very high fields, essentially above 2 Tesla or 1 Tesla. And if it's only when we worked at very low fields that we recovered the zero bias anomaly predicted by the BCS framework. And also, it's the field intensity, so the vicinity of the other vortices, which trigger the occurrence of the conductance modulation we see in the course of BISCO. Okay, so let me just conclude by citing the collaborators. This has been done in a group of Christoph Renner, calculation by Christoph Berthaud, and measurement by Tim Gazdich and Tejas Singar. And as a summary, I can just tell you that what we understand from our measurements is that concerning the heavily overdoped side, the modulation and the presence of the zero bias anomaly are all linked to the vicinity of the surrounding vortices. We don't understand why the zero bias anomaly disappears and gets into finite energy states. We tried to model by decreasing the distance between vortices. And we were never able to get the finite energy subgap states from the zero bias anomaly. So this we still don't understand the strong field dependence of this the vortex structure. Okay, with that, thank you for the attention.
Thank you. One quick question, if there is one quick. If not, we thank you again. This is your diploma.
No, thank you.
Discussing 20